Hi guys, in this video we are going to discuss a question from parallel AC circuit. Here they have mentioned a black box which contains a number of ideal parallel connected elements is fed by a 10-15 degrees voltage source at omega is equal to 1000 radian per second. They have measured the current 2.83 with a phase angle of minus 30 degrees ampere. When the omega is 2000 radian per second, I leads E by 60. So these are the data they have provided for us. If you are new to this expert tutor channel, please don't forget to subscribe. Also, we have done many videos regarding basic fundamentals of electrical engineering. If you like to watch them, I have given the link in the description, so you can always watch them. Okay, without wasting our time, let's move to the explanation. Before that, please pause the video and try to do it in your own. After that, watch the rest of the video, so it would be more useful for you guys. The overall question is, they have provided the sufficient data and they are asking to find the nature and magnitude of the components. So here we need to find whether this parallel circuit is having resistor or capacitor or inductor, or whether it's having these three, or whether there are any two components in these three. So first of all, we need to find what are the elements in this parallel circuit. That's the first question. Find the nature of that. After that, they are asking about the magnitude of that components, the value. So for an example, we can take that we need to find the inductance of that inductor. Likewise, we need to find the capacitance of that capacitor. So we need to find what are the elements are in this parallel circuit. After that, we need to find the magnitude, the values of those components. So first of all, how to find that whether it's having inductor, capacitor or resistor. So for that, we are going to use these two data. If you look this data, as you can see over here, they have provided the voltage source is having the phase of 15 degrees. As you can see over here, the current 2.83 with the phase angle of minus 30, which simply means the voltage is leading the current. So when the omega is 1000 radian per second, we can directly tell the voltage is going to lead this current, which simply means this circuit is an inductive circuit. If you cannot understand what's meant by the inductive circuit or capacitive circuit, I have already taught that in a individual video. If you like to watch that, I have given the link in the description, so you can watch that also. So here you can see that voltage is leading this current, so we can directly tell it's going to be act like an inductive or inductor circuit. So that we can directly tell if it's having a characteristic of inductive circuit, there must be an inductor as well as resistor. Otherwise, it can't be act like an inductive circuit. So we have now found at omega is equal to 1000, it's going to show the inductive characteristic, so that we can tell they are going to be inductor as well as resistor. Why we can tell there's a resistor is, the reason behind that is, actually if there are only inductor, we can directly tell there is minus 30 and 15, so that the phase angle difference is 45, which simply shows that it's not 90. So we can't tell there is only inductor, so there might be resistor and inductor. So in the next case, we need to find whether we are having, what's about this omega is equal to 2000 radian per second, the I is going to be leading that voltage by 60, which simply shows it's going to show a capacitive characteristic, which simply means it's a capacitive circuit, because the I is going to lead when this 2000, when the omega is 2000, which simply means the phase of I is going to be 60 plus this 15, it's going to lead, so we can tell it's going to be 75 totally, which simply shows it's also having a capacitor in this circuit. So from these two data we can figure it out that this parallel circuit is having total three elements: inductor, resistor, as well as capacitor. So now we have found all the three things. So the next question is we need to find what are the magnitude of those components. In a similar type of question, we have already discussed this kind of question for an ideal series circuit elements. Likewise, we are going to follow the same step. However, there are some significant changes because of it has been connected in parallels. So okay, without any further delay, we can go to the steps. So when we are considering about those steps, let's say what are the equations we can write using this one. So now we have found that. So I'm going to draw a simple diagram. There's a capacitor and resistor, and there is a inductor. So these three are in the parallel circuit. Now we can use these types of data also. So let's mark it as this is CR and this is inductor, which is known as L. So the question is we need to use this part first, 2.83 amperes, and they have given the phase angle. What can we do from this data? So when we are considering about this data, we already knew the voltage, and they have given the current, the total current for that three elements. From that, what can we do is we can find, only step we can do is we can find the impedance of this part. When the omega is 1000, we can find the impedance. So I'm going to do that first. So we can directly write it like this. That is going to be equals to V over I. According to Ohm laws, we can directly write this. So if I divide this one, V is going to be 15 voltage, 15 degree, and we are going to divide it by 2.83 minus 30 amperes. If we do so, we can directly divide it by using the calculator. So I'm going to use that. First we need to divide the magnitude of that RMS values. So 10 divided by 2.83 would be 3.534. So I'm going to stop with 5.3, and the angle would be 15 minus this angle. We need to deduct this angle from this one. So 15 minus 30, which will return 45. So this is the impedance ohms. So what are the equations we can write from this one? Actually, we knew that when there are three elements which are connected in parallel, we can directly use one thing, which is that admittance, the total admittance of this circuit would be the addition of each admittance, y1, y2 plus y3. This is an important equation you can use when there is a ideal parallel circuit. So in this case, if I change it to impedance, we can tell it's going to be 1 over z, the equivalent y is equals to 1 over z. We can tell 1 over z1, which is capacitance impedance zc, and the R's impedance, which is zr, plus y3, which is zl. So we can use this part. Actually, we knew the total impedance, equivalent impedance, which is 3.53 with a phase angle of 45 degrees. So we need to substitute the things over here so we can get the answer. So what's meant by this ZC? What's the impedance of capacitor? Actually, we knew that it's going to be careful with these symbols. What would be the thing? It's going to be minus, actually we knew that ZC is going to be minus 1 over omega C into J. This is the total impedance of that capacitor. Also, there is no real part, so I'm going to write only the imaginary part. It's going to be minus 1 over omega C into J. Don't worry about this type of, it look like difficult. However, you can finally use one solved equation, you can directly use that equation and get the answer. So this is the first video containing all these three elements in the parallel, so I'm going to explain how we are going to derive that equation. After that, you can directly use when you are doing any MCQs exam. You need to do very fast, so you can't write these steps too. Okay, when you are considering about the ZR, actually we know the impedance of that Z would be the resistance, only the real part resistance. And after that, we can directly write the ZL. It's going to be 1 over the ZL would be omega L into J. So now we are going to change this J part over that. How we can change this is, if we multiply it by J in the denominator and the numerator parts, we can tell it's going to get J into J, it's going to be J squared. Actually, we know J squared is minus 1, as J is equal to root of minus 1 in the complex number. We can directly tell the J squared is going to be minus 1. So if I multiply J in these two with the denominator and the numerator, it's going to return minus also here. So it's going, this minus is going to cancel it out. So we can tell it's going to be omega C into J. Likewise, if I do for this, we don't need to do for this actually. So 1 over R is going to return. And if I do for this part, it's going to return minus 1 over omega L, as it's going to return J over J squared. It's going to return J squared is going to return the minus 1. So it's going to, the final would be minus J. So from this, if I simplify this, I can directly write 1 over R would be equals to, 1 over R plus 1 omega C minus 1 over omega L J. So this is the equation we can directly derive from this part. In other terms, we can tell the 1 over Z is going to be the resultant impedance. So the resultant impedance would be 1 over R plus omega C minus 1 over omega L J. So the thing is, you can use this equation directly when you are having any MCQ types questions as well as any questions. So some might wonder how we can use this, well, how to remember this equation. It's a little bit similar to the series circuit equation. When we are considering about the Z, the total impedance in a series circuit, we have written like R plus omega L minus 1 over omega C into J. In a series circuit, the impedance would be not admittance, this is admittance, so impedance, the Z would be equals to R plus omega L minus 1 over omega C. Now it's like, it's kind of same change. We have changed the R into that 1 over R, and if we are going to change that L into C. In other terms, we are going to change that omega L into 1 over omega L and 1 over omega C into omega C. After that, we need to change this sign. In the circuit, in the series circuit, we have written like omega L minus 1 over omega C. Here it's going to change a little. So you can use this equation directly. So here I'm going to use this equation directly. So from this is having a complex, we are having in the Cartesian form. First of all, we can use this part. For the first part, we are going to use this one. So if you need the value for these three, so these four things, R, omega, C and L, we can directly change it for polar form and compare with this. So now we are going to change these four components, which means we are going to change this Cartesian form to polar form and substitute a thing and find the value. Either we can do that, or we can change this form. So we can change this part to Cartesian form, as we have already discussed in videos many times. We can either change this one to Cartesian form, or we can change this one to polar form. Both are having the similar types. So in the previous question, I think we have changed this part to polar form and compare. When we are changing this part to polar form, we can directly tell it's going to be root of 1 by R squared plus this part squared. The magnitude of that would be equals to the impedance. We need to change it for impedance, the impedance part admittance part. Likewise, when we are finding the polar angle, we need to take the tan theta, which would be equals to omega C minus 1 over omega L over 1 over R would be equals to the phasor angle of that impedance. So you can either change it for polar form. So now I'm going to change this part to Cartesian form. It looks like easy. Okay, let's do that and check what are the easy things here. So here I'm going to change this polar part to a Cartesian form. So when you are changing the polar form, you can use the calculator directly, or you can draw a triangle, and if you draw a triangle, you can tell this 3.53 is the adjacent length. From that, actually we knew the angle 45 degrees, so we can multiply and get the answer. So here I'm going to use the calculator. Also, I have already done a video which I have already discussed about how to use these things, how to solve these complex number problems using calculator. So I'm going to do it a little bit faster. If you would like to watch that, I will give the link in the description. So please watch that. So okay, first one. So let's try this one. 3.53 with the base angle. Sorry, I think I have missed one thing. Yes, we need to change this one to the impedance so that we can directly check with this one. So I'm going to change this part to admittance. So first of all, we actually knew that 1 over z would be the admittance. So let's change this one. So I'm going to write 1 divided by z would be equals to 3.53 with an phase angle 45. So if I press the equal sign, I have get the answer 0.2. There are 0, so I'm going to neglect that, minus 0.2j. So this is the equation. So now you can see over here that we can now compare this part with these final values. So if I equate these two, I'm going to get 1 over r would be equal to 0.2. Yes, first part I have successfully done with that. The next part, I'm going to compare these two, the imaginary parts coefficient omega c minus 1 over omega l would be equals to minus 0.2. Actually, we knew the value for omega, so you can directly substitute these values and get the value for minus 0.2. If you do so, it's going to be 1000. So we can directly tell it's going to be 1000 c minus 1 over 1000 l minus 0 is equal to minus 0.2. Sorry, 0.2. So now we have done a half part of a question. So the next part is, so here we can find the c and l over with using this equation, because there are two variables, so we need to have another equation additionally, but they have given that also. So they have given the sufficient data, which simply here, when the radians per second is 2000, I leads e by 60. As you can see over here, they have only given the angle details. So we need to use this detail to find another equation. Actually, they haven't provided the whole detail, what's the RMS value to find the total impedance, but from this we can find the polar angle only. So it's enough to do the calculation. So I'm going to find the polar angle of the impedance in the second case when the omega is equals to 2000. So I'm going to write it like this. So z would be equals to, it's going to be the same v over I. Actually, they haven't given the angle, so I'm going to, they haven't given the magnitude, so I'm going to write it like this, v over I. The phase angle here, they have given I leads E by 60. If you take this voltage as 15 phase angle, we can directly tell that I is going to lead that E, so we can tell it's going to be 75. So if I divide it by this, V over I is going to return a magnitude, let's say that is Z, and let's say this is Z vector. So 15 divided by 75, which simply means when you are dividing this, you need to deduct this part, second part. So 15 minus 75, which would return a minus 60. So it's not enough. We are going to change for admittance. So if I consider the admittance, we can tell it's going to be 1 over Z. So which simply means I'm going to write it like this, 1 over Z minus 60. So if I change this part, what I'm going to get here is the 1 over Z will return one magnitude. Y here we can consider like 0. So if I consider like 0, as there are no angle, you need to consider as 0. So 0 minus this part would be plus 60. So I can write this part also minus, it's going to return the 60. So now we have the angle, so we need to compare this part from this part. Actually in this case we don't know the magnitude, so it's difficult. We need to actually use a variable. Let's say we need to take this part as y, and we need to change to the Cartesian form using y cos 60 and y cos 60 plus y sin 60 into j, and we need to compare these two parts. So in this case, so there is another variable. We are going to create another variable called y, the admittance magnitude. So in this case it would be easier if you use this part and change this to polar form and substitute this one. When you consider this only, you can directly get an equation without using this, without getting that magnitude. Similarly, they are little bit equal methods. However, in this question I'm going to change this one to polar form and compare this one. So when we are considering this, how to find the polar form angle over here? As you can see there, if you are having this complex number form, Cartesian form, you can directly take the magnitude using root of 1 over r squared, the real part squared plus imaginary parts coefficient part squared, and take the root of those things. So here what are we going to do to find the phase angle is, we can directly write it like this. Let's say this is tan theta would be equals to the imaginary parts coefficient, which is omega c minus 1 over omega L divided by 1 over r, which would be equals to, actually we knew the value of this part, the angle would be 60, the theta would be 60. When we are considering about the impedance, it's going to be 60, so tan 60 would be directly tell it's going to be root 3. Here you need to substitute the value of omega by 2000, so 2000 c minus 1 over 2000 L, and if I bring that r above, it's going to be, we can find this value of r here, so r is equal to root 3. Now we have 3 equations, so you can solve that and get the final answer. So if you solve that, you are going to get the r as 5 ohms. So like that, we need to substitute these two values over here, and if you find that, it's going to be returning the L, the inductor would have an inductance of 2.021 millihenry, as well as capacitance is going to be 297.6 microfarad. I hope this video would be useful for you, and if you have any doubts or if you have any suggestions to improve my teaching skills, please comment it below so I can also try that. Thank you for watching.